Hello, and welcome back. Today we'll be finishing up the collision tests, going over mesh contacts with spheres, capsules, and hulls. These tests will rely heavily on two main things. The first is a paper by Pierre Terdiman, and the second is the hull versus hull test we already did. There's plenty to cover, so let's begin. Starting at the new supporting additions, we'll be using a structure to cache vertices and do compare and sort operations on. We'll also be using a structure that allows us to delay contact creation with triangles for spheres and capsules. These both will be covered later, but for now they are here. Also, there are some new functions, one for calculating the surface plane of a triangle, and some barycentric coordinate calculations. The barycentric coordinates I will be going over more in depth when doing GJK, as they lie at the heart of the implementation. For now, though, the barycentric coordinates will be used to check for what feature the triangle is being contacted on, whether it be a face, an edge, or a vertex, as well as retrieving the closest point. Starting with spheres and Pierre Terdiman's paper, I will not be covering the paper in full, just the final implementation of the algorithm. But it is a great read and very informative to the problem at hand and why the decisions made are what they are. The algorithm starts by processing the mid-phase list of triangles. I believe the first pass is also done in the mid-phase in the paper. The processing step first checks if a sphere's center is on the negative side of the triangle plane. If so, the triangle is skipped and the algorithm continues to the next triangle. If the triangle is on the positive side, next we want to compute the closest point on the triangle. We'll be using the barycentric function and supply the sphere center as the query point. With the closest point returned, we calculate the span between the center of the sphere and the point, and then simply check if the distance is greater than the radius. If so, there is no collision. Next, we'll want to delay any contacts that are not directly on the face of the triangle. We always want to prioritize face contacts over other feature contacts. However, there is no guarantee the face contact triangle will be processed first. The paper goes into more detail about this. If any of the barycentric weights fall at or below 0, we do not have a face contact, and the current information is cached for later processing. Should we have a face contact, we go ahead and generate a contact manifold and contact point similar to sphere versus hull. The normal is the reverse of the plane normal, and the interpenetration is simply the distance minus the radius. After calculating the collision information, the triangle vertices are added to the vertex cache. The cache will be used to invalidate delayed contacts. After the first processing loop finishes, we then sort the list of delayed contacts by the shortest distance from the sphere to the triangle. Once the sort is finished, we begin the final loop and create any delayed contacts that are still valid. As previously mentioned, if a vertex is found in the vertex cache, this invalidates the collision and the delayed contact is skipped. This is aimed at helping to avoid problems like internal collisions along connected triangles. After checking the delayed vertices, should the contact still be valid, we go ahead and create a contact manifold and point in a similar manner as before. This time, however, we'll want to use the direction between the closest point, which is somewhere along the boundary of the triangle, and the sphere itself as the normal instead of the plane. However, as a fallback, if the numbers become too imprecise, the surface plane normal is a viable alternative. After the list of triangles is processed and all contacts are generated, return the result and we are finished with sphere versus mesh collisions. As previously mentioned, the tertium paper will be carrying us a lot today, and it turns out you can extend it to be used with capsules very simply. However, it may not be the most efficient. First, start by setting up some paperwork, and then once that is all set, we'll go ahead and copy over the code we just wrote for sphere versus mesh. Instead of being just a for loop, we'll turn it into a functor that takes one of our segment points and then call it for each point. Essentially, we're going to be using the virtual spheres on the capsule and checking along the capsule segment for collisions in the same manner. However, there are a couple of caveats. The first is that when we call the test segment contact function, we want to clear the list of delayed contacts. Second, instead of using the segment point as the origin for the center span calculations, we instead want to project the closest point back onto the line segment. This is the part in the theory video I stumbled on explaining. However, the idea is we basically ping pong the closest point off the triangle and back onto the segment in order to test all triangles down along the segment length. For a very long capsule, you would miss triangles in between segment points without the projection back onto the segment. But with that, we can simply move on to the last test for today, hulls versus mesh. So finishing up with hulls, for this one, we're moving away from the paper we've been using and reaching back into our hull versus hull code theory. To reiterate the idea, you can think of a triangle as a flat hull, and as such you can extend that to be any polygon is a flat hull, and then extend that to convex polygons, and so on. When looking for separation between a convex hull, we fall back to doing a full SAT, which is basically a brute force feature check. We can leverage this idea with our flat hulls and create a data structure which is able to handle partial hulls. Then we can augment the SAT function to work with the hulls that have partial feature sets. This collision algorithm heavily relies on SAT as well as convex decomposition. The algorithm I'm still currently working on. However, for triangles on a common plane, they are able to be combined into a suitable polygon for testing. The algorithm starts by getting each set of convex polygons called a face segment. The face segments will be tested against the complete hull using the SAT snapshot function. Then, just like hull versus hull, we evaluate our query information and handle accordingly. Testing for edge contact first, then test the complete hull, and finally use the partial hull to create a contact manifold if needed. Once that is finished, clean up any buffers should you have them, and then return the result. I would like to note it does not make me happy to have left hull testing as such a major black box, considering the complexity of it in light of the overall collision engine. However, these black boxes will be uncovered very shortly. But that should wrap up everything for today. I appreciate you sticking around this long, and I hope you've been able to pick up something. either from this video or any of them in this series so far. As promised many times, after this I will finally be moving on to covering the supporting algorithms that really put the collision engine on their backs. I will first be starting with GJK and the theory thereof, as well as moving on to the implementation, then following that up with SAT. By then, I'm hopeful that the decomposition algorithm will be ready. However, if it is not, I will be going on to the contact resolver to show how to handle all the data we've been generating here in these tests. So there's plenty to come. Stay tuned, and I shall see you in the next one. Thank you, and have a good day.